Derivatives is an odd word. Sometimes you will hear differential equation instead. Differential sounds like difference, and that's what we're going to be talking about. We're going to be trying to talk about the forever small. So in integrals, we've already done forever addition. Now we're going to start to look at forever division, forever small. And with those two different pieces, we'll be able to break things up forever small and add things up forever many. So we have a combination. Those are the two sides of calculus, looking at forever. We have Sir Isaac Newton here. Sir Isaac Newton in a quote to start our day: "No great discovery was ever made without a bold guess." We have formalized our ability to guess in this class, right? We're going to go through that process of thought today with this new exploration and remind ourselves that we're just doing the same strategy for every single one of these questions. Let's talk a little bit about Sir Isaac Newton. Anybody here ever hear of Neil deGrasse Tyson? I love Neil deGrasse Tyson, right? Neil deGrasse Tyson has a big romance here with Sir Isaac Newton. His man, Sir Isaac Newton. Sir Isaac Newton and him go way back, because Sir Isaac Newton figured out so much that we rely on today for physics, right? Discovered the law of optics, understood that white light actually has every color within it. Set the equations for motion down on paper for the first time. Force is equal to mass times acceleration, F equals ma. With that, he was able to derive the field of gravity, understand how the planets and entire solar systems orbit, and developed integral, which is our area, and differential, what we'll do today, calculus, pretty much on a dare when he was sent home during a pandemic and epidemic that was affecting London at the time. I wonder if we all can relate to, being stuck at home during an epidemic. So all of that, then turn 26. So you are all learning a subject that was invented by somebody who was about your age, our age. I'm 30, so it's about halfway between us, right? That's where we're at. What are you looking at me like that for? You didn't think I was 30? What do you think I was? All right, so let's recap a little bit about what we did last time. So what we're talking about, remember we got equations when we were talking about integrals, right? We talked about how we could take certain graphs, like we started with this graph, where we said it was going across at negative 32. This is the actual acceleration of gravity, negative 32 feet per second per second. That's the actual number. You can get it from a physics class, any experiments you want, right? Like we said, we're going to take this, we're going to fill it with area. That area steadily increased. So if I want to graph how it increases, that gets something that steadily changes. That was what we called our velocity. So we went from acceleration to velocity, then we tried to add up a bunch of area in the velocity. That increased more and more as I went on, so the graph for that was something that went quicker and quicker. That got us our position. And at the end of that exploration, we came up with an equation that said I can determine how things fall if I drop them, and that equation is 1/2 of negative 32, so negative 16, t squared. So this is an actual equation. It means if I take this pen and I drop it, which it has low battery, so I'm not going to do that. If I drop it and I wait 2 seconds, I can figure out where it is by plugging 2 into that equation. It will have fallen that far. It's a literal, real-world, actual equation. All right. Today we're going to explore how we can use that position function, right? The position function is this one, x of t, where I'm at based on time, and our knowledge of slopes. Slopes we know as being a change in something, a change like speed. How we can use all of this to combine and connect the equations and the pictures that we had from last class. Now note, we're going to try to figure out how fast something is falling. If you look at your notes for Monday, you already have that answer. That answer is negative 32t. Right? That's what we got when we were looking at how quickly the thing went down at an angle, negative 32t. That means if I drop this, wait 2 seconds, and plug in 2, I'm going negative 64 feet per second. This thing is traveling at 64 feet per second after I drop it and wait 2 seconds. So we have this answer. We, however, are going to try to figure this answer out backwards up the story. Okay? All right, so let's try some things. So we have our position function. This tells me where I am at. I know it's going to graph like a parabola. That's why there's a nice graph of an arc here. We want to figure out speed at a moment. Anybody here have a drive-in today? Anybody commute like I did? Yeah? So if you looked at your car speed at any moment, did it ever say like, I don't know how fast you're going? Right, it was like, we always had a speed, right? Every moment I looked at it's got a speed. Now notice for a moment that it also was something that could change a whole bunch. So it wasn't like, well, you left at 7, let me do a calculation. All right, you're going at about, like, it was just, you are now, speed, right? Speed right now. Notice for a moment that that is not an incredibly easy calculation. In fact, it's a paradox, one that we've explored already, right? Because if on my commute, somebody could have taken a picture of my car, right? They could have taken a picture of my car. Do we live in a Harry Potter world where pictures move? No, once I've got a picture, pictures stop, right? So that means that at every moment, you could take a picture of my car, and in that picture, my car is not moving, right? Because pictures don't move. That means that at every single moment on my commute in, I was not moving, yet I got here. Did you catch that? At every moment, you are not moving. But we know movement happens. Why? So we're going to explore that. All right, so let's try to put algebra, some numbers around this paradox. Let's see what's happening. All right, so we know that velocity is going to be change in position divided by change in time. If I want to know how quickly I am moving at 2 seconds after I drop something, right? 2 seconds after it's dropped, then let's look at what's happening. At time equals 2, then I am currently at whatever I get when I plug in 2. All right, so far so good. If I want to compare what I'm getting at 2, like where I am, against where I am, I'm comparing where I am against itself. All right, so that means that in that exact moment, I am comparing where I am versus where I am. Got it. How much time has passed in a moment? But there's no number for that. What's the actual amount of time that passed? Zero. There's no time, right? That's what happens when I say how much time is between 2 seconds and 2 seconds. Well, let's plug all this in. So I've got negative 16, plug in 2, squared, minus negative 16, plug in 2, squared, divided by 2 minus 2, equals 0 divided by 0. Speed is impossible. At least speed in a moment, right? Because I've done speed plenty in algebra, but in algebra I had to ask how long, like I traveled this far, this much time, right? So you had a certain amount of time we were playing with. If I start talking about the speed at a moment, no time has passed. How did I move? Yet my speedometer on my car always tells me that I'm moving. We've got a barrier here. So the answer is that algebra is not the tool to tell us, because I'm trying to hit a forever small amount of time, aka no time passing. I'm trying to hit forever small with a tool, algebra, that is not made to talk about moments. It's made to talk about big things, differences. And I don't have a difference here. All right, so that's the problem with velocity at a moment. Algebra is not the tool. All right, so let's try going back to this question through the method that we've established in this class. We'll do the method of exhaustion. All right, I'm going to need calculators out. Y'all are going to help carry us. You ready? If I want to know how quickly I am going at t equals 2, I can compare that against something really close. Think about like old-timey policeman speed traps, right? Trying to like, we get a little stopwatch, we'll click on the stopwatch, we'll click off the stopwatch, we'll do a little math, figure out how fast we're going. We're going to try that approach. All right, so we're going to compare time 2, which is 2, against something else. Time 1, which is, we're going to find something close to 2. All right, what's a number that's a little less but close to 2? What we got?
1.9 remaining.
1.9. Now that would be actually is 2.
Oh,
but we could simplify that to just 1.9. Are we good with just 1.9? We'll start off pretty decent. What was it?
1.8.
1.8 would also work. So let's do 1.9, just because it's going to help make the pattern obvious. But you could literally verify this with 1.8, and I'd encourage you to do it. 1.9. All right, so let's go ahead and plug this all in. So we're going to start with my position at 2 versus my position at 1.9. And I'm going to look at how far I moved in the amount of time that passed. That's going to be, I plug in 2 minus plug in 1.9 divided by 2 minus 1.9. Why don't y'all tell me what that gets?
Negative 62.4.
Negative 62.4. By the way, also, if you want, we can do a little manipulation of some numbers here and find a way to make this a simpler calculation for next round. We'll factor out a negative 16, and we'll be left with 2 squared minus 1.9 squared over 2 minus 1.9. That'll help us kind of do some of this math a little faster. Oh, don't stretch, just move. All right. So how fast do we think we are going at 2 seconds? Because this is not right? This is close, not right. Close, pretty good, not right. What do we think is the true answer? We're not sure? Okay, let's do some more div. Big fan. All right, let's now compare 1.99. Now I'm looking at 100th of a second that has passed. All right, so that's looking at where I'm at 2 versus where I am at 1.99 over how much time has passed between 2 and 1.99. Through the same equation we had above, we could plug in negative 16, 2 squared minus 1.99 squared divided by 2 minus 1.99. What do we get for that?
Negative 63.84.
Negative 63.84. Closer. Anybody want to wager a guess about what we are actually traveling at 2? Sure. What do you think?
I think that it might be 63.9.
Maybe 63.9. I like that. Anybody else? Any different guesses? What do we think?
Negative 64.
Negative 64? Good. How do we figure out? Oh, let's try another data point. All right, let's do it again. We'll look at 1,000th of a second away. All right, what do we get? Please.
Negative 63.984.
Negative 63.984. All right. So not 63.9, close. We got past it. Oh, bummer, right? All right, what do we think? What's everyone's guess?
Negative 64.
All right, what do we think? People, we got agreement? Show of hands who agrees. All right. Who can prove that it's negative 64 and not negative 64.1? Because this gives us data, gives us insight, does not give us an answer. We can continue to run this closer and closer and closer and closer, and we will continue to have better and better and better and better evidence that it's negative 64. How do we prove it's negative 64? Well, I can't make a forever long list of data. That's going to take too long, unless y'all want to. Anybody here tired from having to do all those calculations? Yeah? Now y'all know why we call it the method of exhaustion. We only got 3. We're supposed to have it forever. You want to keep going forever? No, we don't got enough time. So we need something else that instead of trying to find data along the list, we understand the list's behavior And if we understand the list behavior, we can figure out where the list is converging, where it is closing in on, what its actual true value at the end is. So making a list, in other words, plugging in numbers, does not work. It can give you insight, sure, but it's the same as the area. When we plugged in numbers to try to get better and better guesses of the area, that didn't work either. We had to take a step back and realize, like, we're going to have to play with some variables. And we're going to have to be okay not locking those variables down, because if we lock them down, they're not changing anymore. And I want to know how it changes. I want to know where it approaches. Let's keep this nice and general. Some time versus some other time. This again is this is velocity. I'm pulling it right from what we're trying to figure out, right? I can plug in those times, negative 16 t2 squared minus negative 16 t1 squared over t2 minus t1. I can even factor out a negative 16. That's what I showed on the last step. I have budgeted plenty of time in this lecture to answer questions. So at any point, if I lose you, I'm looking to you to just raise your hand. We'll talk it back through. At this point, because I'm seeing less pencils move, give me a thumbs up if we feel like we understand where this formula came from and we could explain it to somebody who wasn't here today. If it's thumbs down or thumbs sideways, that means you have a question and I'm looking to you to ask it. Go ahead, please. Sure. What we are trying to find is some way of figuring out the velocity at time 2. And that velocity equation, we know since algebra is going to be change in position versus change in time. So all I've been doing is I'm looking at where was I at time 2 versus where was I before and how much time passed. Can I simplify this more? All right, I saw, yeah, so you can tell me how. Let me see a hand. Yeah, please. We can factor the top. All right, so factor in the top, which again goes back to the visual algebra, the area model. We can factor it using any tool you want, but we're recognizing that we can make this, I think it's T2 minus T1 times T2 plus T1, right? Is that all good? Yeah, okay. So pause here for a moment. Again, if anyone needs a reminder on where this came from or why, it's a good time to ask a question. Please, yeah. You guys ask. Go ahead.
Where did 16 come from? Where did 16 go after the?
Yep, so right here, because we had it in this, and then that one as well, you can make this like a plus and drop the parentheses if you want. You can work that paper on your end. But we're just simply saying there's a negative 16 affecting the front term and the back term. So I'm going to pull it out front, factor it out, and just recognize that I've left some stuff behind. Does that feel good? Cool. Other questions? All right. This is your idea to factor it. What do we do next? You're gonna be my help for the next couple lines here.
You can flip with the T2 minus T1 right?
So you're saying I can cancel this and I can cancel this.
Yeah.
All right. You ready for this? Why? Yeah, there we go. Good answer. Bad answer, but truthful answer. All right. Why can we do this, please?
It's almost like we're dividing it. So it's like you're dividing 1 divided by 1 is equal to something.
So a number divided by itself is 1.
Yeah.
Give me an example of that.
So I guess like if the top equal to, then the bottom's going to equal to that.
Times 2 divided by 2 cancels out to 1.
Yeah.
Give me another example.
6 divided by 6.
6 divided by 6 cancels out to 1. Not if we're following? All right, does that mean that every number divided by itself is 1?
Yes.
Oh, oh, so close.
Is 0.
Ah. Is that 1?
No.
No. And isn't the whole reason I'm doing this because I want to make the times the same? See, here's a way of kind of capturing that. If you cancel those, in algebra, what you would have had to write to take care of this fact is you would have had to write equals negative 16 t2 plus t1 so long as t2 is never t1. Right? You would have had to write something along the lines of saying, so long as that wasn't 0. Well, I want to make them the same thing, so I've just gotten in my own way. So what can we do instead? Here's the difference. As it's written on the paper right now, this is algebra. But we know we're trying to make a list of approach, right? Let's go back one slide and remind ourselves. We had data, 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 getting towards what we thought might be our perfect answer, right? So here's my question for you. At this step right here, we would have had negative 16 times 2 minus 1.9 times 2 plus 1.9 all over 2 minus 1.9. Let's check back in real quick. Help me out if we can. 2 minus 1.9 would be 0.1 divided by 0.1. Let's double check. 0.1 over 0.1 is 1. That one worked out. I could do it there. I could cancel it there. That worked out great. Let's do the next line. In the next line, we would again have negative 16 times 2 minus 1.99 times 2 plus 1.99 over 2 minus 1.99. 2 minus 1.99 would be 1/100th. 100th divided by 100th is 1. That works out just fine, right? I'm seeing a lot less people nodding. Are we all good? The number divided by number, or the number divided by itself is 1. We just can't do that with 0, right? And in this approach, was I ever doing 0 divided by 0? No. So what it means is that I could have gotten the same data from an equation after I simplified as I would have gotten from the original. We can't just cancel things that look the same on the top and the bottom. However, if we remind our audience that we are trying to look at the numbers along the approach, because along the approach, I never have a divide by 0 error. It's perfectly fine. So what we need to do to our notation to show our audience is we need to remind them that we're considering a limit. So we need to have limit notation all the way through this to remind them that we're not looking at what I get, we're looking at what I approach. So I need limit notation in every single line. Then once I have this notation, now we can make an argument that says I can cancel these away. And when people come to us and they say, but it could be divided by 0, we say, no, it can't. Because I'm not asking what it is, I'm asking along the approach. And along the approach, it's always a little different. So along the approach, we get the exact same data from this equation. Oh, but we need to remind our audience that this is an approach. It's a limit. So again, I'm going to pause here for a moment. Is anybody confused as to why I'm allowed to cancel that term away, but I would not be allowed to cancel that term away in algebra? We feel all right, please?
I just want to double check. So the idea is that you're kind of sort of using the fact that 2 and 1.9 are repeating, like it's technically approaching 2 and it kind of is 2.
So I'm not at 1.9 repeating yet. Right now I'm just at 1.9, closer, 1.99, closer, 1.999. So I'm grabbing distinct data along the way. I'm not trying to do forever approaching. I'll do that in a moment. But as of right now, everything on this paper is justified by the data we did on the last slide. So I could just get numbers, the numbers follow what we think the numbers should work, and they do work. Are we all right so far?
Yeah.
Okay, good. There's nothing tricky I'm doing. I literally could have gotten the same data on the slide before if I simplified. And I'm allowed to simplify on the slide before because I never had to divide by 0 on the slide before. So I'm just saying I can gather data from a simpler looking equation. That's all it's saying. Did you feel good? You got a question? It's not like I'm restricting the domain. It's that I'm trying to explain to my audience that I don't want to consider the equation. I want to consider the list I build using that equation. So the limit means make a list that approaches forever closely, right? The same way that we used it all the way, every time we've ever used it, we're just trying to talk about some method of getting close and close and close and close. Because sometimes we can't hit answers directly, we have to hit them close. All right, let's run this thing to an end just so we can see what the conclusion is. This right here is my data equation. That gives me the same data. Same data, we proved it on the slide, same data. So now if I want to make time 2 get forever close to time 1, at the end of it getting forever close, time 2 is the same as time 1, right? All right, so negative 16, time 1 plus time 1. That's negative 16 times 2 time 1s. The time we were considering was 2 seconds. Negative 16 times 2 times 2 is, oh, that's kind of what we all knew from the slide before was going to be our perfect answer, right? Right there. Like we knew it was at the end of the list. We knew it was, we could see it happening. We just couldn't prove it. So how did we prove it? We didn't stay in the list. We looked at how the list was behaving. We used the behavior to go past the list and land on perfect. Good. We lost the limit notation. How come? Because at this line right here, that right there, that was the calc logic. We said the calculus logic make T2 forever close to T1. Forever close to T1 means is T1. So at that moment, I didn't have to look at what do I get as I get close. We knew forever close means is.
Okay.
So it worked out in our math because I had created a new structure to gather data from, and that data didn't have the problem at the end. It didn't have a divide by 0 error. I didn't need it. Very, very interesting. Yeah. Yeah, because it's right here. It's the same thing we were just talking about. This calc logic here says if T2 gets forever close to T1, at the end of getting forever close, it becomes the same thing. Do we feel all right with that? So that's why I replaced T2 with T1, because this said I'm going to get forever close. And I said, well, forever close, the same thing as is. Go ahead. See, it worked for us replacing it here, because here I had found a data structure. I found a structure that got me data that didn't have a divide by 0 error. I got the same information without a divide by 0 error. The other one gave me the same information with a divide by 0 error. I couldn't have used that one to get to the end. This one I can use to get to the end. It's all right there. So if you look in a traditional math textbook, this is like, I think in my Calc 1 textbook, this comes up on page 80 of about 500 pages worth of content they'll learn in the semester. So in other words, it comes up in like the first 20% of the class, the first fifth of the class. But it is a barrier for students all the time because they look at me and they go, so I can just plug it in? And I'm like, kinda? Like kinda you can plug it in? But you can only plug it in if you know why you're allowed to plug it in, and if you've changed the equation so that it works if you plug it in. And then, yeah, you can plug it in. They're like, oh, good, so I'll just plug in 2. And then they get divided by 0 errors, and they wonder what happened. And it's like, because you tried to dodge the story. Like, it's all about the story. You need to let the story evolve and avoid those errors, not by trying to hit the problem dead on, but recognizing calculus gets us answers, and sometimes to touch forever, we have to take a roundabout path. Yeah?
So is this a story how we get the power rule?
Close. We'll actually touch more on the power rule on Friday. I mean, we've already touched on it anyways, which is if you want to do integrals on down, then you can use power rule. We know that derivatives take us kind of up that path, so there's got to be a reverse to that, right?
That's like negative 16 times 2t is very similar to doing power rule. Negative
Yes,
16.
and we'll really quantify that on Friday. Good, that's exactly right. All right. Now, to help really anchor this concept down, what I want to show you is I want to show you how Newton was the first one to really I'll say first one, just about the first one to really work these kinds of equations. But I want to show you how Newton actually did it. I think it's a very intuitive process. It's brilliant. The problem is that it's inherently wrong. We'll see what, like it inherently starts from a really bad assumption that we've already gone over plenty in this class. But it works to tell that story very beautifully. So let's do it together. So I've just got the solution we did on the side, right? We already did that one. So you don't have to copy it down. That's everything we just did. I just wanted you to have that as reference when we look at how Newton approached this problem. Because what Newton decided to do, and keep in mind, he's like 26 at this point, right? And the world has been beating their head against this problem for 1,700 years. Pretty much on a dare, Newton goes back to his house, comes out 3 months later and says, I've solved it. And everyone's looking at him like, you gotta be kidding me. And they start looking at his work, they're like, oh, but that work doesn't make sense. He's like, yeah, but it gets the right answer every time. Every time it works. Let's see what happens. All right, so let's play. Here's what Newton did. Newton said, you know what? I'm gonna look at t, we'll say time is 2 again, but I'm gonna look a little off. I'm gonna look at where I am just after. And I'm going to use the exact same equations. The story here is very clear, right? Instead of looking at 2 seconds, we're going to look at 2 seconds versus a little bit off of 2 seconds. Like, that's okay, right? T plus dt. What's dt again?
Delta t.
Delta t, but it's more, delta t is algebra, big sizable change. dt is infinitesimal change, forever small change. So we're looking at 2 seconds and then the moment after 2 seconds. Let's pause for a moment. Are infinitesimals real numbers?
No.
No. So we are already off to a horrible start, right? We've already started saying, let's use a number that doesn't exist. Bad. Right? But let's humor Newton. We'll go ahead and run this on through. All right. Using the exact same equation we had before of negative 16t squared, we're going to plug this all in. Negative 16 t plus dt squared. Oh, sorry, that should be a subtraction symbol. Minus negative 16 t squared divided by t plus dt minus t is just dt. Excellent. All right, let's just kind of smash some algebra here. All right, we're going to have negative 16 times, this is going to distribute on through, we're going to get t squared plus 2t dt plus dt squared minus a negative would be plus 16t squared over dt. We can distribute. How can we simplify from here? Who's got an idea? Please.
And there is 16 dt squared.
16 dt, how do I get rid of the dt squared?
I mean, it's 16 plus positive 16.
Oh, the t squareds? I can get rid of the t squared. Yep, let's get rid of those. I like that, right? Negative 16 t squared plus 16 t squared cancels away. So now we are left at negative 32 t dt minus 16 dt squared over dt. What can we do here?
Take out the dt.
Divide the dt out, right? We can make that nice and explicit. We'll factor the dt out. dt negative 32 t minus 16 dt over dt. We're going to do with the dt's?
Cancel out.
Are you sure? Because the rest of the mathematical world wasn't sure. Because Newton canceled them away. There's the same thing on the top and bottom. But we already said there's no such thing as infinitesimals. What's the true number for forever small? 0. So Newton was over here in his proof going, sure, let's just cancel these away. They're the same. And everyone else is going, you just did a divide by 0 error. And he's going, yeah, but it worked. Right? Like, frustrating. Frustrating. Now, we know why this works now. Right? We know why this works. It comes from this stage right here. Here, we were allowed to cancel the denominator and the numerator because we went through a big logic story of limits and approach and data collection, and we justified that it's not actually 0. Newton over here just called it something else and tried to fool us. Not exactly the same. The math world wasn't confirmed yet. It gets the right answer, and the physics people were all like, works for me, let's build stuff. All right, dt gets very, very small. We are left with, think about it like limits. dt becomes 0, we're left with negative 32t. So he got the exact same answer that we know is correct, but his story was off. The logic didn't work. And the logic is just as important because we got to convince people we're not doing a divide by 0 error. Like, it doesn't make sense. We've explored that. So, summary. I like this approach for its intuitive value. It helps make sense out of what we just did. We're looking off of the time a little bit. Where are you going? I got you for like 2 minutes. The amount of math I can do in 2 minutes, you got no idea. All right, hold tight. So anyways, but we've got like, that's the story. This captures the story very well, the intuition. But we need that limit notation. And I'm reminding you all because when it comes to quizzes and tests, if you just do algebra and you don't write limits, I can't credit that because you're trying to do calculus brain with algebra showing. That doesn't, you got to show me calculus if you want me to follow calculus. So make sure we're including the limits at every step in our work if we need it. But the story is nothing too much. So some things we're going to use, just some terminology to keep in mind. Difference quotient. Big, complicated, scary name for exactly what we've been playing with. What's the difference quotient? It's your... It's the difference, subtraction, quotient, division. Subtraction and division is what you've been playing around with slope for forever. It's how you've been doing speed for forever. So difference quotient just means find the change, the rate of change, the speed. Okay? Nothing too much there. Derivative. Let's actually pin down what a derivative is. A derivative is the limit of the difference quotient. It's us looking at speed and trying to run it to perfection, perfect change. Exactly accurate, using calculus logic. Sometimes we can give a formula like this. This tells the same story. Let's take a look, right? It's just like having t plus delta t. So like h just means how far I'm off. So it's saying I am at x and a little off compared to when I'm on x, and then I'm looking at the difference, which we called h. So it's looking a little bit off h-wise compared to where I started, divided by how much h is. So we can write it using this notation. But there's actually a lot of different notation that we'll use in the class depending on the story I want to communicate to you. Sometimes I'll use m subtangent because m we know to be slope, right? And if I'm talking about perfect slope, that's slope at a point, that means I'm just barely touching the graph. So sometimes we'll talk about the slope of the tangent line. We'll get more into that before test 2. F prime with a little apostrophe. If you see an apostrophe on anything in your homework problems, that means it's a derivative. It's a notation Newton would use to say this is a derivative right here. The derivative based on this curve. dy dx. This is a forever small change in y versus forever small change in x. So you can think of this like your slope, but it's the slope when I did the limit. It's at the end of the perfect. It's at the end of making it forever small. So next class, as you were mentioning, we have a power pattern for integrals. We have shown that integrals take us from acceleration to velocity to position, and the derivatives take us from position to velocity to change in velocity, aka acceleration. Like we go back up the chain. So does that mean that we can solve these problems doing the reverse of the power pattern? And the answer is yes. Does that mean that these are exact opposites? We're going to try to find out Friday. I've been around for a little bit. If you have any questions, stick around.